Hello everyone, welcome to Wave Properties. So I'm just going to present this for you. If you look at where this has been posted, you'll notice there's quite a few video links in there. And during the course of the presentation, you'll find there's lots of different little video links and that sort of thing. So let's have a look. So we're looking at wave properties today. So here we go with wave properties. So what we're going to look at is what waves are used for, transverse, longitudinal waves, what's the difference between those two. We need to know especially what's a transverse wave, how do the particles move, what's a longitudinal wave, how do the bits of that move. The basic idea about how do you know whether something's transverse or longitudinal. So this little video link here for you, it's Brainiac's one, a little bit of fun. You pause me and then go back and find the video link. You can see I've posted the video link or shown you the video link at the bottom here. Obviously, because it's a Loom recording, you can't click on that, but it should be on the Google Classroom post. So have a little look at that. So now you've looked at the Brainiac's video, you can see that the energy is clearly passed along, isn't it? So that's actually how waves essentially work. They pass energy from one place to another. So if you looked at the Mexican wave, the energy starts at one end and it gradually moves its way along right to the end. So it's the movement of energy. And you'll notice that the people in the Mexican wave, they move up and down, but what they don't do is they don't start at one end of the grandstand and go running down the other end. It's actually just the energy moves. And it's a really good idea and a really good model of actually how waves work. So you can see that the energy gets passed along, but actually the parts of the wave just stay where they are. Right, let's have a look at them. So this is what we're going to look at today. We're going to look at what waves are used for, what transverse waves are, what longitudinal waves are. We're going to look at some keywords that you need to know the definitions of. So amplitude, frequency and wavelength. We're going to look at something called period of a wave, and then we're going to have a look at some calculations of a wave equation. So you'll need a calculator. Right, okay. So two basic types of wave. If we're not talking about longitudinal and transverse, we've got two basic types of waves. So we've got mechanical waves. These are waves that basically pass through a material and cause vibrations inside it. They're like sound waves, seismic waves, the earthquake ones. Anything on a string or a slinky or a spring, water waves, that sort of thing, yeah? And then there's electromagnetic waves. So these are things vibrating electrical magnetic fields. So these move through space, they don't need particles to travel. This is how light gets here from the sun, because you know there's no particles in space. So if electromagnetic waves had to pass through a material in order to travel, light wouldn't get here from the sun, because sound is a mechanical wave in that it needs to pass through a material by vibrating that material. That's why we don't hear the sound from the sun. So electromagnetic wave, light, passes through space. A mechanical wave, like sound, has to vibrate something in order to travel. That's why you don't hear the sound of the sun. That's clever, isn't it? Right, okay, so electromagnetic waves. So these are our two basic types. Right, so let's have a look at a little slinky. Remember slinky, long, springy thing, right? And if you've got one of those at home, brilliant, you can have a go at this. So if you made those two waves on a slinky, what you would get is you get the top type. The top type, what you're doing is the energy moves along, but you're making like a little pulse. So push it backwards and forwards. Watch my hands. So you're moving it backwards and forwards, and as you move it backwards and forwards, what you do is you vibrate the particles as they move along. And you'll notice that the energy moves along the wave, a bit like your Mexican wave did, yeah? Energy moves along the wave. The second type is like a side-to-side wave, so that sort of wave, yeah? And the parts of the wave move at 90 degrees to the direction of travel. You've got one type that does that, and another type essentially that does that. So parts of the wave move up and down while the energy moves in that plane. So you'll notice there's different parts. So in your book, make a table. Transverse waves, longitudinal waves. They're both very different. They've got one thing really important in common. is that they both carry energy. How they carry energy, slightly different, but most importantly, they both carry energy. That's the whole point of waves. They're energy carriers. Okay, we're going to collect some information now. So let's look at the first type, which is transverse waves. And I'm going to make that gesture all the time, yeah, transverse waves. So there you go, first type. There's the definition. Write down the definition. Oscillations of a transverse wave are perpendicular to the direction in which the waves transfer energy. Perpendicular. Okay, so I love this little GIF. You like this. There you go. Ooh. So you can see that the parts of the wave are moving up and down, and the direction of travel is going along. So perpendicular, yeah? Bendy hand, perpendicular, yeah, to the direction of travel. And also, if you notice that the little dots, the black dots, are not actually moving along, they're just moving up and down. And if you look at one of them, you can see that little particle moving up and down, and that's transferring the energy. So there's your type of transverse wave, perpendicular to the direction of travel. You're going to fed up with me doing that. There you go. Example, the electromagnetic waves. Yeah, remember, they don't need particles to travel. Waves on a string, waves on a wire. If you play a musical instrument that you pluck, like a guitar, ukulele, piano, anything like that, where you're actually making a wire vibrate or a string vibrate. You might play the violin or something. If you play the violin, what you're doing is you're making that cat girl, wherever it's made from, you're making it vibrate, yeah? So that's all to do with making that vibrate. So that's the first type of wave, transverse. Right, second type, like these. These are longitudinal. So still carrying energy, but the oscillations, so the wiggles, are parallel to the direction in which the waves transfer energy. That sounds a bit fancy to say. If the energy goes one way, the particles go backwards and forwards in the same direction. So if the energy is going like that, my bits of my wave are doing that as they go along. They're not going up and down, they're going vibrate, all as they go along, yeah? So direction of travel. Now, what if you watch with this? This is weird, this GIF, because if you look at the red bit, it seems to push it along, and it gives you this weird sensation that the whole thing is actually running along, but it's not. And just watch one particle, and you can see them move along. Also notice there's like a darker bit, and then like lighter bits. So, and then if you drop down and look at the diagram at the bottom, that gives you the idea a little bit more. So you've got bits where the particles are close together, bits where they're far apart. So where they're close together is called a compression, because they're compressed together. And then a bit further apart, they're called an expansion. Sometimes you see expansion called a rarefaction. So RAREFRACTION, rarefaction. So that's where the further apart is compressions of rarefaction. So longitudinal waves. So that is actually, remember with the longitudinal wave, that's actually travelling through something that needs particles. So, example, sound, essentially. Needs something to travel through. Yeah, sound can't travel through space. So you can see it's like a parcel effect. So you've got one thing. So you've got one thing that does both. There's no other waves apart from one type that can be transverse or longitudinal. Everything is either transverse or it's longitudinal. There's only one type of wave where it could be both. Yeah, and that's these ones, which is seismic waves. So seismic waves can be transverse or they can be longitudinal. So if you think about the destruction that those two different types of waves could cause, a transverse wave, as it goes up through the ground, so to my top hand is the surface of the earth, right? Here comes your longitudinal wave, right? Right, tapping on the surface of the earth. The building is going to jiggle up and down like that, isn't it? Right? If you're a transverse wave going through the earth, you're going to move like that, yeah? Think how much destruction that's going to do at the surface. The most building damage, like the photographs, is actually caused by the transverse wave, so that you can see them make a difference. So seismic waves can be both. Only ones, only seismic. Right, so go back, now see if you can find this video. So this video, you can see is the GCSE Science Revision Man, and it's called Transverse and Longitudinal Waves, yeah? So you have to pause me and then go back and find the link for that, and then work your way through that, okay? So go find the video. Right guys, welcome back. Hope you got any additional information from that. You can see that on that video they refer to it as rarefactions as well, but some places call it compressions, some places call it rarefactions. I thought it's probably a good idea to give you both words. Okay, right, let's move on then. Done that, parts of a wave. Now, you need to know all of these things. If you look at that diagram, that's the sort of diagram you expect to be transverse wave, but you can take a sound wave and you can put it in something called an oscilloscope. You can Google that. And then you can find out how that works. So this is your basic diagram. So you can see it gives you that shape, doesn't it? So you've got a dotted line in the middle, which is essentially like the zero line. So that's zero displacement. So displacement moves tells you how far something is from a point. So how far is it from zero? So the wave can go up and back down and then below the zero line. So it's a bit like water waves, still water. You can see the water goes above and below that line. So there's some words you need to know. And after this diagram, there are definitions that you can write down. So draw that in your books, really neatly get that zero line in. So if you've got using your exercise book, use the lines on the book, yeah? So what we're going to do is we're going to label this. You might remember some of these labels already. So here we go, parts of the wave. First part, if you look here, I've picked the top of one wave and the top of the next one. So those are two identical points on the wave. And the distance between those two identical points is actually called the wavelength. There's a special symbol for wavelength, which looks like a Y that's upside down. It's called lambda. So Lambda, lambda. And that's a wavelength. It's the difference between two identical points. Now what you need to know is you need to know what the height of the wave is called. So from the dotted line to the top of the wave, there, the dotted line to the top of the wave, that's the maximum height, yeah? That's also the same distance as from the dotted line to the bottom as well. That's called the amplitude, amplitude, definition on the next slide. Okay, that's the amplitude. Then what we're looking at is the names of the bottom bit and the names of the top bit. So that guy there at the bottom is called a trough, and that guy's called a peak, yeah. So you've got a trough and a peak. Okay, both flash for you. Woo! Now, one complete wave is for the wave to complete one whole movement. So if you start right back at that point there, right back on the screen, let me move my cursor. There it is. If you start there and then you follow the line of the wave, it goes up, down, down. And when you get to there, what it's done is it's gone up and back down. What it hasn't done is completed one full cycle. So it's only gone halfway. That's half a wavelength. So I've got to go down to the bottom, all the way back up to there. Once it gets to there, yeah, that point there where my cursor is, that is one complete wave. It's gone through one complete cycle, yeah. That's one complete wave. So on my diagram, you can see I've got 1, 2, and a bit complete wave, yeah. But that's really important. You know what a complete wave is, because that helps us with definition of something else. Right, so you can pause me if you want to. Next page. Yeah, key terminology, you need to write it down. You need to know these. Displacement, wavelength, amplitude. Yeah. Okay, write those down. Pause me because I'm going to talk. Right, next video. So this is properties of wave. There is a link in Google Classroom for this. So this tells you all about different things, different terminology. Yeah, so have a little look at that. It's about 20 minutes. No, it's not. It's about 10 minutes. Yeah, it's quite a short video. So go watch that. Okay, next one, key terminology. Look at this little formula. Yeah, you need this is on the formula sheet. Whoa, there's not many. This one's actually the formula sheet. So, period. It's the time taken for one complete wave. Do you remember what the complete wave was? There you go. Complete wave. And do you remember from here what complete wave was? Right, let's go back. Yeah, right. So the time taken for one complete wave to pass a point. So if I was standing on the beach and I was watching the waves go, the time it would take one whole wave to go past me, that's the time it takes for one complete wave to go past you is called the period. Sometimes it's called the periodic time, but it's called the period. That's the time it takes for a complete wave to go past you. So, if you want to know how many waves you therefore get in a second, yeah, what you're looking at then is the frequency. So frequency is the number of cycles, the number of waves per second. So, for instance, if I'm standing on the beach, on the seafront, Little Hampton, something like that, watching the waves come in, and in one wave goes past me in half a second, the number of waves in 1 second would be, that would be 2. Yeah, one wave takes half a second. Therefore, in 1 second, I would get 2 complete waves. So that's literally the difference. So in your calculator, to work out periodic time, if you're given a frequency, you've got to do then 1 divided by the value of the frequency. Also, if you're given the frequency and they want you to work out the periodic time, you can actually swap the F with the T. So those numbers just swap over there directly. So if you want to work out the frequency and you know periodic time, you can do 1 divided by the value of the periodic time, and that would then give you the frequency. And honestly, I promise you, it works. So you can practice that. That works absolutely fine. So, wave equations. You need to know this wave equation. This is not on the formula sheet yet. And what we do is we've got some sample calculations, and I'll tell you some of the pitfalls and things that people get wrong. So, formula not on there. Learn this formula. Wave speed frequency times wavelength, sometimes referred to as V equals F lambda. Yeah, V equals F lambda. Wave speed is frequency times wavelength. Meters per second, hertz, meters, right? You have to have those units. You don't have those units, your calculation is not going to work, right? Meters per second, frequency, wavelength. You might have kilohertz. Kilohertz is 1,000 hertz. If you get a number given to you in 1.5 kilohertz, that's 1,500 hertz. Okay, work it out. Got to be in meters. Get centimeters, you've got to convert it. All right, make sure, right. Calculation. So, pause me and then have a go at the calculation. First thing you've got to do every time, I'm going to give that to you now, is write down the pesky formula. Right. Okay, and then what we're going to do is going to go through the answers. So pause me and then have a go at working these out, right? Okay, and pause. Work them out. Right, let's do the answers then. So, first thing you've got to do is always box underline. So, first things first is, what do I need to find out? So, what they asked you to find out? They asked you to find out the wavelength, yeah? Right, and what else? Write down the formula. What do you know already? You need to find out wavelength. You know the speed of sound, and you know 660 times a second, right? So that's the frequency. So what you do is you write down your formula. Please write down the formula first. Don't try and rearrange it before you put the numbers in, because in an exam, there is a mark for correct substitution. So first things first, you need to write down the formula. Now, learn it one way. V equals F lambda. If you learn it as a triangle, fine. Yeah, but just write it down, please. V equals F lambda. This tells the examiner that you know what you're doing. V equals F lambda. Let's put the numbers in. There you go. The speed of sound is 330 equals 660 times lambda. Now, a mistake a lot of you will make now is you need to get lambda on its own. You need to solve this. So, the mistake a lot of you make now is you then go 660 divided by 330. Oh, no, wrong. It's 330 divided by 660. Look, 330 divided by 660. You want to get the 660 out of the way. It's got to go under the equals bridge. Under the bridge. Yeah, you get it out of the way. So 330 divided by 660 will give you 0.5 millimeter. If you, at this stage here, then go and put 660 divided by 330 into your calculation, you will get the wrong answer, but at this point the examiner will give you 1 mark for correct substitution. If you don't write down your workings, yeah, you will in fact get 0. If you don't do the maths correctly, you will get 0. If you actually write substitution, you will get 1 mark. That could be the difference between a 5 and a 6, or a 4 and a 5. Please write down your substitution. So that's enough of me moaning. So 2A, speed rate.